Hello dear students, welcome you all. Today we are going to start with low pass filters, and we are going to start with Butterworth low pass filter. You can see here Butterworth low pass filter is visible. Okay, so actually this Butterworth low pass filter that we are going to discuss here, it is named after British physicist Stephen Butterworth, who has invented it in 1930. Stephen Butterworth, right? So this filter was invented by Stephen Butterworth, right, in 1930. This is the simplest type of filter that we are going to discuss here. Okay, you can see the circuit diagram here. It is visible here in this image. Yeah, this is the circuit diagram of this filter, and it is of first order. So we will discuss this circuit diagram first of all, and then we will drive the expression for the transform function in all the filters, whether it is uh, low pass filter, high pass filter, band pass filter, or band reject filter. We will first of all design the circuit of first order, second order, and higher orders, and then we will find a mathematical expression for the transform function that will give us the relation for the gain of the filter, how the gain of the filter depend upon different components of the circuit, right? So the circuit of this first order filter is visible here. This is operational amplifier, you can see here. uh, this is plus VCC minus BE. This is feedback resistor. This is R1, right? This is the resistor R, and this is a capacitor C. This is the input signal which is applied on this terminal, non-inverting terminal, and this B1 represents the voltage at this node, right? So, and this is the loop. This is the loop, and current I is flowing in this loop. So we will explain this circuit first of all. So you can see here, if I took this loop exclusively, then this loop is, you can see here, it is, this is, right. So this is B in, this is R, this is the node B, one is the voltage at this node, and this is further connected to the positive terminal of the operational amplifier, right? Right. So if we look at this loop, I current is flowing from this direction toward this. This is negative, this is positive, right? So as it is written here in this image, you can see here B1. According to voltage divider rule, the voltage B1 that is appearing at this node is given by iota XC upon R minus iota XC, right? This is, you can see here, this is, this in this image you can see it is minus iota. This is iota XC. XC is a capacitive reactance. B in is the input voltage, R value of this resistor R, iota, and XC, right? Now how we have calculated this voltage B1, right? So this voltage can be calculated by applying the Kirchhoff's loop rule in this loop, right? Yeah, we can say Kirchhoff's voltage rule. We have two type of two Kirchhoff's rules: Kirchhoff's voltage rule and Kirchhoff's current rule. That is known as junction rule, and this is known as a loop rule. So if we look at this loop, right? So B in, negative, positive. Now it is, current is flowing in this direction. So obviously it is positive here and it is negative here. So negative positive, it should be negative positive. So it means it is opposite. So B in minus IR voltage here, Now we are measuring this voltage with respect to ground, and this is negative. So B in minus IR minus V1 is equal to 0. This is the complete loop, right? We are assuming here that nearly zero current is flowing inside the input, this input of the operational amplifier. Because we know in case of operational amplifiers, the input impedance is very, very high. So when the input impedance is very, very high, so nearly zero current flow at this terminal, right? At this terminal and at this terminal also, it means toward the operational amplifier. So we can ignore this current. So the loop rule is this, it is mentioned here. So from here, B1 is equal to V in minus IR. It is written here, equation number 2. So also, if I extend this again, then it will become B in minus IR and B1. What is the B1 voltage? It is, I have written here, plus I iota XC. Now you can see here the same amount of current I that is flowing from here. It is going to this direction because the current going toward this side is nearly equal to 0. So I current is flowing through the capacitor. The capacitive reactance is XC, right? So it becomes I into iota, it stands for imaginary, and XC minus iota XC. When we multiply it with minus, then it becomes plus. So B in minus IR plus I iota XC. So it gives I is equal to B in upon R minus iota XC. This is equation number 3, right? So I think it is clear now. The value of the volt is appearing at this node B1 is equal to this. Now we are putting the value of I in this equation number 2. So when we will put, we will get this one, right? B1 is equal to minus iota, that is mentioned here, right? Now we are going to put the value of XC. XC is what? Capacitive reactance. I have told you in the previous lecture also that X is capacitive reactance and it is 1 upon 2 it is pi Fc, right? 1 upon 2 pi Fc. Now here F is the frequency of the signal, C is the capacitance of the capacitor. So if we put this here, then we will get B in upon 1 plus iota 2 pi RFC. We are putting it in the denominator and denominator, and then after solving we are getting this, right? So we know in case of now we are applying the theory of operational amplifier, because here if I talk about this operational amplifier, now we are using this amplifier, operational amplifier, in the non-inverting mode, right? So when we are using operational amplifier in non-inverting mode, negative, positive, right? And right. So it is RF, right? And it is virtual ground, it is R1, right? And this circuit is connected to the this filter circuit. So I can say it is connected to B in. Yeah, B1 voltage is appearing at this terminal, right? So this is B1 appearing here, and this voltage appearing at this terminal B2. This was B2, right? So B output in case of operational amplifier operating in non-inverting configuration, it is given by 1 plus RF upon R1 into B1. This is the expression that we have derived in the theory of operational amplifiers, right? So now we have found the value of B1, and we can put this value here. So then we will get the value of B output. So in this next step, you can see here in this equation, B output is equal to 1 plus RF upon R1, B in 1 plus iota 2 pi RFC, right? So then after we will solve this equation. So then we will solve this equation. B output, B input will be taken toward this side. B output upon B input, AF upon 1 plus. Now AF, what is AF? AF is 1 plus RF upon R1. Clear? We know, as I told you, that in case of operational amplifier, B output is equal to AF into B input, right? B output is equal to AF into B input, right? So we can see here B output is upon B input is equal to AF upon 1 plus iota 2 pi RFC. So I have took it as AF upon 1 plus iota F upon FH. Now FH is equal to, I have put the value of FH. FH I have taken, FH is 1 upon 2 pi RC, right? So that will give us this expression. If I put 1 upon 2 pi RC, 2 pi RC, then if you take it here, then again the same thing will appear here. So B output upon B input, that is equal to gain as the function of frequency. So if I took the magnitude of this equation, because this is in the complex form, clear? So if I took the magnitude of this expression is in the complex form. So B output upon B input magnitude, this will give you AF upon 1 plus iota F upon FH. If you take the magnitude of this side also, then it will give you what? AF upon it will give you AF upon 1 plus F upon FH square whole term under the root. Clear? This is what? B output upon B input in a magnitude form. This is the transform function. Clear? That I have talked about in the beginning of this lecture. So our task was to drive this expression. Clear? To drive the expression for the transform function. Clear? So here fh, that is equal to 2 pi RC. This is called cutoff frequency, highest frequency that is allowed to be passed by this filter, because it is a low pass filter. So you can see here in this diagram, this is pass band and this is stop band. So this frequency, the frequency will that will be fh, that is this. Clear? This frequency here, it will be fh. Clear? At this point. Clear? fh. So all those frequencies which are higher than fh, they will be attenuated, stopped. But when you can see the different conditions at very low frequencies, when f is very less than fh here, then we can ignore this, right? It means under root 1 means 1, so B output upon B input is equal to AF, gain. Same, so it is AF, right? When f is equal to fh, 1 plus 1 2, so AF upon under root 2, 0.707 AF. When f is equal to fh at this point, clear? It is 0.707 AF. And when f is very high, then higher than fh, in that case, clear, I can you know, if f is higher than fh, then we can ignore this fh. Clear? So it will become, obviously the denominator will be a very high term. Clear? It will be greater than 1, right? So when I divide AF by something that is greater than 1, right? Obviously, I will get a number that is less than AF. So B output upon B input will be less than AF when F is greater than FH. So as we go toward this side, the value of the gain will go on reducing and ultimately it will become 0. So this is the frequency response of Butterworth low pass filter or first order. Clear? Here the rate of the fall of the gain is minus 20 decibel per decade, right? We will see that in the second order and higher order filters, this rate will be different. Particularly if we talk about the second order low pass filter, it will become double, minus 40 decibels per decade, right? Roll off rate, yeah, frequency, attenuation rate. And this is pass band. Here the frequency response is flat. So this Butterworth filter is also called as a flat response filter. Clear? So this is about the Butterworth low pass filter, and it is for first order. Why we are calling it as first order? We are calling it as first order because here we are using only one functional unit. Clear? This is only one functional unit. Clear? R and C. But if I use two functional units, then obviously it will become second order low pass filter. Clear? So this is all about this low pass filter. We have derived the expression for B1 because we know according to the theory of operational amplifier, B output is equal to 1 plus RF upon R1 into B1. So first of all, we found the value of B1 appearing at this node. We put the value here. Then after we simplified this equation and we converted it into a transform function, then we got a transfer function this, and after getting its magnitude, this is what we got, right? And this is the frequency response, right? So this is about the Butterworth low pass filter of first order. In next lecture, we will go to the second order low pass filter. Clear? Thank you.